All right, so today we're going to cover chapter 3 in the textbook. We ran out a little bit of time on Friday last week. There was a fire alarm, and we had to evacuate the room. So there was one thing on variation in categorical variables that I didn't get to cover. The big point there is that if one category is dominant, there's little variation, whereas if all of the categories are equally represented, then that's maximum variation. And so I think if you check out the reading in your textbook, you'll get an idea of this concept. If you have any questions, you can come visit me during office hours as well. All right, so chapter 3 is all about numeric summaries for numeric data. So everything we cover today applies to numeric data. It doesn't really quite work for categorical data, all right? And the big idea here, the big idea for this, today's lecture is that you might have a data set with thousands of observations. Okay, if you have thousands of observations, you might not want to you might not care about all the details of all 1,000 observations. And you might have one data set with several thousand observations. You might have another data set with several thousand observations. And if you want to compare this data set to this data set, or just this group to this group, if you've got thousands of rows of data to go through, it's just too much information for our brain to process. So what do? We want to boil down this data set to just a few numbers. We also want to boil down this data set to just a few numbers. Once we have just a few numbers, then we can start making comparisons that we can process, right? So, for example, let's say we wanted to compare the student body of UCLA versus the student body of USC, okay? At each of these schools, there's thousands of students, right? If the registrar were to or the admissions committee or whatever were to reveal, and they won't, but if they were to just give you all of the raw data, you'd have thousands of, students to read through, okay? And it'd be like, student 1 has, this score on the SAT and, this family income and this GPA and studied this in high school, blah, 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 okay? Student 2 has all of this information. Student 3 has all of this information. It's too much. It's too much info. It's much easier if you just say, okay, the average income of a student attending UCLA was this much money. The average income of a student attending USC was this much money. And you can compare those averages, and then kind of maybe you can then say well, at this point, we're just going to be able to compare those two numbers, okay? Rather than trying to compare, all of these individual students and all of these individual students, we can just say, here's the average for USC, here's the average for UCLA, okay? And that's where we're going to start off here with our idea of descriptive statistics. So let me just kind of write that down. Big idea. Your sample of data may consist of hundreds or thousands of observations. Perhaps even millions, okay? We may not want all of those details. Okay? If we want to make comparisons, it's too much information. So instead, we summarize the data, okay? And so a numeric summary boils down the data to just a few values, okay? Or numeric summaries and I think we're familiar with numeric summaries, you know, just in different contexts. So in college, you're very familiar with the numeric summary known as your GPA. Okay, the GPA is a single value that is supposed to summarize your entire academic career and performance. Okay, or at least in college. And you know, instead of, like, if you were going to apply for a job, you know, the person reviewing your resume probably doesn't care about every single class you took and how you did in every single one of these classes or things like that, okay? Instead, you can just put your GPA on your resume, maybe, if you want to do that, and that will give the potential employer a sense of what kind of performance you had in school overall, okay? But of course, because it's a summary, you lose the detail. So perhaps, you know, there was a quarter where something happened and your academic performance suffered for it, okay? That single number isn't going to tell that story. It just says, your GPA, this number, blah, and that's it. So the strength of a numeric summary is also its weakness, in that it makes your life easier just by giving you a single number. Its weakness is that it's just a single number and it doesn't tell the whole story. Okay, so we are familiar with, you know, a numeric summary that we are familiar with. Example, GPA. Okay, this is a single value supposed to summarize your entire academic performance. Okay. But there is, and as useful as a GPA might be, there's something slightly dehumanizing about saying a person is just a single number, right? And you know, it's not, it doesn't tell the whole story. And I always tell my students that your value as a person is far more than the grades you earn, okay? So, and truly, in the future, your GPAs make very, very little difference in the grand scheme of things. Okay. All right, so that's GPA. You know, if we want to compare one nation to another nation, okay, in terms of economic prosperity, you know, we have summaries like the GDP, gross domestic product, which is supposed to be a measure of how much economic output a country has, okay? And so you can, you know, rather, you know, trying to summarize something as complicated as an entire nation's economy is a difficult thing, okay? But you can just say, oh, well, if we want to compare the United States to, I don't know, some other nation, Brazil, you might be able to look at the GDP as something that tells part of the story, okay? We can say, oh, look how much China has changed over the last 50 years. We can say China in, you know, 1967 versus China in 2017. The GDP of China back then was this. The GDP of China today is this. We can say, comparing, you know, just these two numbers, we can talk about, how much the economy of China has grown, without being weighed down with all of the details of every single, sector of the economy and things like that, right? So, other numeric summaries, or we might call these summary statistics. Include GDP. This is a way to summarize economic, prosperity / output. Okay, but of course, it doesn't tell the whole story either, right? If you're into sports is filled with numeric summaries. So if you're, if you watch baseball, they have batting average, on base percentage, slugging percentage, on base plus slugging, all of these things. Basketball, you have, shooting percentage, field goal percentage, free throw percentage, 3-point percentage, rebounds per game, all of these things. And they're just numbers that are supposed to measure kind of the performance of a basketball player, or football, the quarterback gets a passer rating or things like that. They're just summaries rather than having to watch the entire game and giving some kind of subjective analysis. You can say, this is the number, therefore this. Okay. So these are these are examples of numeric summaries that are specific for certain applications. All right, GPA only makes sense in an academic concept, okay, or a context. If you start talking about your GPA at, at the bowling alley, like, you're gonna lose some friends there. Okay. All right, but anyway, we have numeric summaries that. These are kind of like generic numeric summaries for any that work in any context, or set of numeric variables. Okay, and we have summaries to describe center. And these, I'm sure you've heard of these before, the mean and median. And we have summaries to describe spread. And you may or may not have heard of these. We have the standard deviation, and the IQR. IQR stands for interquartile range. All right, we have some guidelines, and the guidelines say that for certain types of data, you should use these values, and for other types, you should use these. But the truth is, here, let me just write it. So these are some guidelines for which summaries to use. Okay, and these are just guidelines because the truth is, all of these numeric summaries can be used for any numeric data set. Okay, and so the suggestion is if the data is skewed, we prefer to use median and IQR. Okay, so skewed being, left skewed, right skewed, things like this, right? Okay, and if the data is symmetric, again, these are the guidelines. We may prefer to use the mean and standard deviation. I'll write it out. Okay, and again, symmetric being something that looks like this. The reasoning is that the mean and standard deviation are affected by extreme values. And so for skewed data, extreme values appear only on one side of your data set. And so in that case, they get affected in one direction. Okay, so for skewed data, you have extreme values on only one side. Whereas for symmetric data, you have extreme values on both sides, and so they balance each other out. Okay, and then as far as the for the skewed data, the median and IQR are not affected by extreme values. Okay. However, again, all of these numeric summaries can be used for any numeric data set. So even if it's skewed, you can find the mean and standard deviation, and there's nothing wrong with that. And even if it's symmetric, you can find the median and IQR, and there's nothing wrong with that. It's just, these might be our preferences. All right, and so we'll, let me just kind of demonstrate finding some of these values here. If I can flip to the next slide. All right, so we'll pretend, we'll say imagine, we're going to make up some family. We'll say imagine the Johnson family. The Johnson family has, we'll say, 4 kids and their ages. The ages of the Johnson family will go in reverse order. 16 is the oldest, then there's a 15-year-old, 14-year-old, and the youngest is 2. Okay, so we can make up a backstory for the Johnson family or how this happened. And now I'm making a dot plot. So here's a dot plot. And so for the dot plot, I just put dots where each child goes. Okay, so I got a 2, here's a 14, here's a 15, and here's a 16. Okay, and so to calculate the mean, I think you guys know how to do this, is you add them up, right? You add up your x's and you divide by n, right? So this sign means to add up. And so what do? I get 2 plus 14 plus 15 plus 16, bless you. We divide by 4. I get, when I add these up, I get 47. I divide this by 4 and I get 11.75. Good? Okay, and so the conceptual definition of the mean here is that it is the balance point of our data. So what we do is we say, okay, well, imagine this being a seesaw, okay? And I've got these weights at 2, 14, 15, and 16. If I want the thing to be balanced, I put my fulcrum right here. This is my balancing point. Balance point at 11.75, that's where the seesaw stays balanced, right? Because this guy is so far away, he exerts a lot of leverage. These three are a little bit closer, so they don't exert as much leverage, even though there's three of them and there's only one over there. Okay, does that make sense? Okay, and so, you know, the mean here is 11.75. So, you know, here's the question. If somebody's asked, what is the average age of kids in the Johnson family, does it feel right to say that the average age is just under 12 years old? Doesn't quite feel right, right? So to only say, you know, the average age of children in the family is, you know, is under 12 years old, is just under 12 years old. Okay, that is a correct statement. However, it doesn't seem to capture the whole picture. Okay, to only say this does not really tell the whole story. And I mean that's the deal with summary statistics, is that the summary statistic might not tell the whole story. And I don't know, what would we say the average age is? Okay, it's kind of hard to do, especially when you have these outliers. Okay, so that's the Johnson family. Let me just kind of compare it to another family with 4 kids. So let's we'll imagine the Smith family. Okay, and let's say, you know, let's say the Smith family and the Johnson family, they were friends, okay? And so their 4 kids, again, 16, 15, and 14, and 13, okay? So the ages, so, you know, the 3 older kids, they all grew up in school together, BFFs. The youngest over here was just picked on by the other 7. Okay, well, anyway. Or 6. So we have the Smith family, and so in this case, if I make a dot plot, okay, the mean here is 13 plus 14 plus 15 plus 16 and I divide this by 4, the mean here is going to be 14.5. I forgot the symbol for the mean. X bar. This is the symbol for the mean of a sample. Okay, so we have X bar, and so I would go drawing my thing 13, 14, 15, and 16. You know, my balance point right here, 14.5. And so comparing the Smith family to the Johnson family, we can see that, you know, in the Smith family, using a mean of 14.5, saying the average age of the children in the Smith family is 14 and a half, that seems adequate. That seems like a reasonable thing to say, okay? You know, is a reasonable thing to say. And what we can see is that comparing the Smith family, let me just flip back to the Johnson family. You know, the 3 oldest children, they're the same in both families, but in the Johnson family, the youngest is only 2, and so that dragged down the mean from 14 and a half down to 11 3/4. Over here, you know, when the youngest is 13, you know, that kind of keeps the mean, you know, in the middle of everything. So the mean is affected by extreme values. And that the mean gets, quote, pulled in the direction of the skew. Okay, so in the Smith family, the ages are symmetric. In the Johnson family, the ages are left skewed because you have an extreme value on the low end. So what's that? I don't know. Yeah, on that side. So you have an extreme value on the low end. No, the other way. Extreme value on the low end, and so that makes it left skewed. Whereas in the Smith family, you don't really even have any extreme values here. Okay. So that is that's the mean. Is this okay? All right. And I'm sure you guys have seen the mean as far as calculating it, but now I've given you a conceptual definition. All right, let's run the clicker, and today will be mostly a kind of a test day. All right. Now I have to set up this class. Stats 10, lecture 4. Okay, so what we're going to do is, let me just get this going here. I'll just give you some easy questions here. So for this first one, turn on your remotes, and when you turn them on, they should say stats 10. They should find the base. I don't know, do they? No? Does it say no base, or? It says stats 10. What's that? Okay, great. Okay, if you've turned on your remote and it says stats 10, then that's a good thing. I'm hoping everybody has their remote registered with CCLE. Okay, if you registered it with CCLE. So what I'm going to do is today I'm just going to give you some easy questions that everybody should get correct. Okay, And then, and normally I upload the scores just at the end of the week, okay? But today I'll upload them tonight, and then you can check online to see if you've got your points, okay? So just this will be kind of our first test question. Just go ahead and click the button A, okay? So just go ahead and click A, and then looks like you guys are getting your clicks in. I'll upload the scores, and then it should go. Yeah, question.
It says no base.
It says no base, then you probably have the wrong frequency. So I don't know. Check the back of the remote. There might be directions on changing your frequency. The frequency is AA. That's the default frequency. Generally, when you turn it on, the default frequency is AA. And if it says stats 10, then you're in good shape. Okay? So it looks like somebody clicked a B on my poll here. Okay, so this is everybody. So and we got a C in it. Yeah, you guys are just messing with me here. So again, I'll upload the scores. If you have it properly registered with your student account on CCLE, then the points will appear in the gradebook. If the points don't appear in the gradebook, then that means you either don't have your remote registered with CCLE, or I don't know, something's malfunctioning with your remote. Okay, so but if you're, when you turned it on, if it says stats 10 and you've clicked your button A and it looks like everything went through, then we're good.
Does it collide with other class if they have the same base?
So if it does, okay, but my computer will warn me. It will say, you've turned on your base and we are detecting other radio frequency on the same thing. And if that's the case, then it would ask, do you want to change your frequency from AA to something else?
Oh,
so
no, I meant from like other class another time.
I don't know what you're talking about.
Like I have another class that's using iClicker with the same base.
Oh yeah, no. That instructor has their own computer with the iClicker thing, and we have to get synchronized, so that there's no problem there. Okay, all right. Whoever clicked D and E, you're gonna miss out on your point. So just make sure you clicked A. I'm gonna close the. All right, there you go. Okay, I'm gonna close the poll here, and then 154 of you will get your points. Okay, if you haven't gotten a remote yet, please get your remote. And so the way the points work is you get 1 point for just clicking a button during lecture at some point, and then you get another point for each question you answer correctly. So if I ask 2 questions during a lecture, then there's 3 points possible. 1 just for participating and clicking the remote, and then you'll get another point for each question you answer correctly. All right. Okay. So anyway, we'll do that. And again, generally I ask tricky questions during clicker things. So if your clicker average is like 60%, it's okay. All right. The clicker portion of your grade is very small, and I purposely ask the tricky questions during the clicker, so you're exposed to the tricky questions, and when you study, you'll be prepared when they reappear on the exams. All right. Another aspect that we want to talk about when describing data is the spread of a data set. Okay. So again, we're talking about a numeric variable. And so let me just kind of, so the idea here with spread is, are the values that we see in the data, are they very similar to each other? Or are they spread out? Are they quite different? Okay? So just imagine the ages of people. Okay? So imagine the ages. So let's say we visit a 2nd grade classroom. Okay, so you go to a 2nd grade classroom in the United States, and looking at the students' ages, how old are these kids? they're like 7, right? In second grade, pretty much everyone is 7. You might have a few 6-year-olds, you might have a few 8-year-olds, but by and large, most everyone in that class should be 7, okay? So almost everyone is 7. Is 7 years old. A few 6, a few who are 6, and a few 8, but probably 90-something% 7 years old. Okay, so the ages here, we have very low spread, very little spread in the ages. Okay, you can probably get away with, and if it's second grade and 7-year-olds, probably not very much spread in clothing size either, right? You can probably buy like a youth, I don't know, small or whatever, and it'll probably fit most of the kids there as well, okay? But we're just talking about ages, very little spread in the ages. Okay, now think of this classroom, okay? And think about the ages of the students in this classroom. Okay, how much spread do we have in the ages in this classroom? Okay, so as far as ages go, we've got a bit more spread, right? So we have a little more spread. Probably around, I don't know, 90% of you will be aged, you know, between 18 and, I don't know, 23, okay? And, you know, there's also going to be a large, you know, more students who are, you know, older than that, okay? Okay, and the rest will be older. You know, will be, you know, older or whatever, okay? But by and large, you know, majority of students within a certain age range, okay? So here we got, you know, a moderate amount of spread. All right, imagine we go to the DMV, okay? And we're in the waiting room at the DMV. Okay, what kind of ages will we see at the DMV? DMV is the Department of Motor Vehicles in California. This is where you get your driver's license and renew your vehicle registration, things like that. You're going to see all sorts of ages, right? So we got all sorts of ages. You have teenagers getting their license. You've got young adults and middle-aged adults. Young adults, middle-aged, seniors, pretty much everybody, right? Even like, you know, if parents are taking their children along because you can't leave your kids in the car, they're going to be there, all right? And so as far as the ages go, you've got lots of spread in the ages. Right? And so this is kind of the idea of spread for a numeric variable. We're looking at the numeric variable age, and we're talking about the spread. And so overall, the concept, low spread, means that the values in our data are not very spread out along the number line. Like if we were to create a dot plot, they all kind of show up in the same area. The values are not very spread out, or another way to think of that is the values are similar to each other. On the other hand, high spread, the values are spread out on the number line. or the values are very different from each other. Okay, so far so good? All right, and so I'm going to introduce this concept of standard deviation. The standard deviation is a very important value that we use in statistics, and all it is, the big picture idea behind the standard deviation is that it is a way to assign a number to the spread. Okay? So the standard deviation is a way to quantify the spread. So on the previous page, we said the spread in the second grade classroom is small. In the college classroom, it's medium, and at the DMV room, it's high. Okay? These are kind of just vague terms, right? Instead, we can take the standard deviation, instead of saying spread is small, medium, high, we can say, oh, in the second grade classroom, the standard deviation is 1.5. In the college classroom, the standard deviation is 4.3. I'm just making up these numbers. Don't ask me where I'm getting them. And then we go to the DMV and we say the standard deviation is 22 or something like that. Okay? So rather than just saying small, medium, high, we can say 1.5 versus 4.5 versus 22 or something like that. So we're giving a number to the spread, and we can make comparisons that way. So the standard deviation is a way to quantify the spread. So instead of saying low spread and high spread, we can say the standard deviation is 1.4, or the standard deviation is 22, okay? And depending on the context, a standard deviation of 22 could be huge or it could be small, okay? Because it's very possible to have other data sets where the standard deviation is, thousands, okay? You can have very large numbers. And so, if we're talking about standard deviation of the volume of different stars, okay, that's going to be, big numbers, right? So that's all it is, okay? I'm going to give you the way to calculate this, but don't lose sight of what the standard deviation really tells us. It's just a number that tells us about how much spread we have. Okay, and so we can think of, one way to define the standard deviation is we'll say the standard deviation, I gotta work quickly here, is equal to the square root of the variance. Okay, so here's a term. And what is the variance? The variance is equal, and I'm going to just put in quotes, the average squared distance from the mean. All right, and we'll go through some steps on calculating these things. The symbol for the standard deviation, I'm going to just abbreviate this SD, is S, and the symbol for variance is S squared, okay? Because the variance would be the average square distance from the mean. Standard deviation is the square root of that. Square root of S squared is just S. Okay, don't mix up your square roots and your squares. Okay, square root of 9 is 3. The square of 9 is 81. Okay, that's it. Sometimes students get those mixed up, and that messes everything up. All right, so let's just imagine two more families. Okay, both families. So we got the Baker family, and we've got the Thompson family. Okay, both families, we'll say, have 5 kids. The average age is 9, and the ages are symmetric. So you might think, well, the numbers might look the same, but they don't, okay? So let's say the ages in the Baker family, we've got a 1-year-old, a 5-year-old, a 9-year-old, a 13-year-old, and a 17-year-old, okay? And in the Thompson family, the ages are 7, 8, 9, 10, 11. Both families, 5 kids, average age is 9, and the ages are symmetric. Does life in the Thompson family look like life in the Baker family? No, right? And the Baker family, you know, the oldest one's thinking about college, and I don't know, whatever, and the youngest is in diapers, okay? And the Thompson family, you know, they're all kind of, they probably all play together. Okay, so if we ask just a simple question, here, I'll make a clicker question out of this, but we'll, you know, I'll just give you the answer. Okay, if I said, which is going to be bigger? Okay, is the standard deviation of the Baker family bigger than the standard deviation of the Thompson family? Or is the standard deviation of the Baker family smaller than the standard deviation of the Thompson family? Or is the standard deviation of the Baker family equal to the standard deviation of the Thompson family? Right? So your choices are A, B, C. Go ahead and click in what you think. You can talk to your neighbor, but actually, we're going to run out of time. So just click A, everybody, all right? Click A. We got to go. We got to move on to the next thing. So everybody should click A, and then I'll upload these scores. And if you had a remote today and you clicked buttons, you should get 3 points, okay? So just get your clicks in. I'm going to cover this last topic here because we're going to run out of time. All right, so let's talk about calculating the standard deviation. So we got the Baker family kids, okay? And the ages are 1, 5, 9, 13, and 17. And we said the variance can be defined as the quote average squared distance from the mean. Okay, so these are the ages of the kids, and so step 1 is to find the mean. The mean, you add those up, you divide by 5, you get 9. Can I close the poll here? Everyone got A? Okay, well, I'm going to go ahead and click stop, and everybody gets their points. All right, so the mean is 9. Step 2 will be to find the distance from the mean. Okay, how do we do the distance from the mean? Well, we just say, okay, how far is 1 away from mean? And we say, oh, it's 8 below. How far is 5 from the mean? It's 4 below. How far is 9 from the mean? Well, it's right at the mean, so its distance is 0. How far is 13 from the mean? 9. 4 points away. How far is 17 from the mean of 9? It's 8 units away. So that is the distance from the mean. Then we're going to get the squared distance from the mean. So whenever you square a number, it's always going to be positive, right? So we do -8. -8 squared gives me 64. -4 squared gives me 16. I square all of these numbers, oops, and I get 0, 16, and 64. These are my squared distances from the mean. Now we want to take the average squared distance from the mean. Okay, I put average in quotes here because we're going to add them up, and instead of dividing by how many we have, we divide by 1 less than that. We divide by n minus 1. So we add up and divide by n minus 1. So I do 64 plus 16 plus 0 plus 16 plus 64. Okay, and I have 5 numbers, but I'm going to subtract 1 from that. So this gives me, when I add all of these up, I get 160, and instead of dividing by 5 for the average, I divide by 4, and I get 40. So 40 is my quote average square distance from the mean. This is my variance. My variance is this. My variance is equal to 40, and therefore my standard deviation is equal to the square root of that. The square root of 40 is equal to 6.3246. That's my standard deviation. If you did the same process, and I leave it to you as an exercise to do this as you go over your notes, find the standard deviation of the Thompson family. So if you find the standard deviation of the Thompson family, you will get the value 1.5811. And so now, rather than just eyeballing it and saying the spread of ages in the Baker family is larger than in the Thompson family, you can look at the standard deviations and say the standard deviation of the Baker family is 6 point something, standard deviation of the Thompson family is around 1.6. This number is bigger than that number, therefore the spread in the Baker family is more than in the other family. Okay, so that's what we have. Yeah, I leave this to you as an exercise. It should be fairly easy for you guys to do. Okay, we'll see you guys on Wednesday. Have a good night.